Ladies and gentlemen, let's continue with our module in heat transfer. We are busy with the textbook of Cengel and Ghajar, and today we're going to start with chapter 8, which is on internal forced convection. In terms of forced convection, there are quite a number of chapters on forced convection. We've done chapter 6, which was on the fundamentals of convection, chapter 7, external convection, and today we start with internal convection. Right, so what is the difference between external convection and internal convection? Now the easiest is to explain it like this. If this is a free stream at a certain temperature T infinite and V infinite, and we would look at what happens close to the surface, then we will have the velocity boundary layer doing something like that, and that velocity is V infinite, and that velocity there is 0.99 V infinite, which means that that is the boundary layer thickness. The very important thing to realize is that there is what we call a free surface, because this velocity and that velocity is the same. If you just go far enough from this solid surface, which can be a flat plate or whatever it is, then you're going to get to V infinite. Then the same with the temperature distribution. If we want to look at the temperatures, let's suppose that is the temperature on the wall, and this is then the temperature distribution. Then we're going to have that temperature there. Well, it's not a vector, it's just like that, T infinite, and somewhere we are going to have 99% of it, and that's going to be the thermal boundary layer thickness. So the very important thing to see is that this velocity and that temperature is the same as that of the free stream. And that is therefore being called external convection. Okay. Sorry, I made a mistake here. This chapter is on internal forced convection, of course. We've already completed the external forced convection. So that is for external convection. Let's look at typically what happens with internal forced convection. With internal forced convection, there are always at least two boundaries, and if that is the free stream velocity and the temperature, then the velocity distribution, the boundary layer is going to develop like that. And we know that that is the boundary layer thickness delta. And this velocity distribution here is going to be parabolic. And that velocity there is actually 2 times this velocity V. Let's rather make it a V than a U, like that. 2 times. So you will see that this velocity is much more than that inlet velocity. That is the first thing that is noticeable. And the other thing that is noticeable, if we now look at the thermal boundary layer, I'm going to draw it there just to show it. In this case, it develops quicker than that of the velocity boundary layer, which determines which one is the quickest, the Prandtl number. The Prandtl number is equal to 1, then these boundary layer thicknesses will be exactly the same. So if we look at this, what is important is to see is that usually the two boundary layers meet. The two boundary layer, BL, is boundary layers meet each other. There you can see they start meeting each other. If this geometry is of course short, or short enough, then they might not meet each other, but in many cases they will actually meet each other. So this is internal forced convection. In terms of examples of geometries in which we normally have internal forced convection, we can start with the simplest one, which are for a pipe, a duct, or a conduit. And we need to just make sure that we all use the same terminology when we use different types of geometries. So for a geometry like this, that would be known either as a pipe or a tube, or then more correct, a circular tube, if you've got something like that. What is the difference between a pipe and a tube? Well, the textbook is not very clear about it, but there are some other nomenclature that would say a pipe is a tube which is rough. So the epsilon of D value is significant, while with a tube the epsilon divided by D is approximately 0 for all practical purposes. Then it is called a tube. So at this stage, pipes were casted, and for that reason they started calling it pipes. Right, then a duct. A duct would typically be a geometry like this, and we see it a lot in air conditioning and refrigeration applications, where air is being transferred from one point to another point, obviously from the air handler units to releasing it in a venue like this. And these things are normally quite big, typically 500 by 300, and in many cases much larger. However, usually the air, they carry normally air, and the pressures in them are normally a maximum of 120 kPa. So they cannot take large pressure differences. Pressure difference, of course, if this pressure is becoming higher and higher relative to that of the atmosphere, then there's a huge pressure difference. There's a huge area normally involved, and a large area, if you keep on increasing the pressure, it increases lots of stresses and strains. With a pipe, however, in most cases, the pressures can go up to megapascals and even more. What is also important is that if we've got flow through a tube or a pipe, and this can be very long, and there is no heat transfer, then this temperature, T1, would be equal to T2. So T1 is equal to T2. So the mechanical energy that is being converted because of the friction is negligible for all practical purposes. In one of the previous lectures on the videos, I actually, from first principles in thermodynamics, looked at a few applications, and you'll see that if there's no heat transfer, of course that's now very important, but there's just flow through a very, very long tube, there's obviously friction involved, a pressure drop, so that pressure will be higher than that pressure, but there will not be a significant or a measurable increase in temperature for water and or air. So you need to remember that. Okay, so you've already seen that to know what the flow regime is, laminar, transitional, or turbulent, we make use of the Reynolds number. So for the Reynolds number, for internal forced convection, it is always equal to rho, V infinite, multiplied by a characteristic length divided by the viscosity. So here we make use of the free stream velocity. In the case of internal flow, the Reynolds number is based on rho multiplied by an average velocity multiplied by a characteristic length divided by the length. So in this case we work with the average velocity. Now in terms of this average velocity and temperature, average velocity and temperature, this is not V divided by T, it is velocity and temperature. Maybe I should write it like that. Okay. Then, from the conservation of mass, we can say that the mass flow rate is equal to rho V average divided by the cross-sectional area. And you've already done it in fluid mechanics where you've looked at this derivation, and for a circular tube you've derived 2 terms divided by r squared, 0 to r of the velocity distribution r dr. The derivation is in your textbook. You've already done it previously. So that is equation 8.2 in your textbook. You also know that for laminar flow, the velocity distribution would be parabolic, like that. Parabolic velocity distribution. And the question is now, as I've indicated already, that velocity can be 2 times the average velocity. Let me call it the average. So the question is now, what do we use in terms of calculating the Reynolds number? And the answer is, you need to go through the process of integrating this and determining V average. We'd rather use V average. Okay, now almost in all the cases in the tests and exams and in the back of your textbook, all the problems, you would see that it is very rare that for internal flow we're going to give you the velocity. It is from a practical point of view, you always give the mass flow rate. So you have to go and calculate the average velocity, which is very simple. If it's a circular tube, that is equal to pi divided by 4d squared, and you can calculate that value. Now, that is what you've done in fluid mechanics. In heat transfer, we've got a similar problem with the velocity profile, with the temperature profile. So if the temperature profile is obviously being determined by the wall temperature, let's suppose that is the wall temperature. Remember, temperature is not a vector, so we call that Ts and that Ts. And in this case, the fluid is warmer than that of the wall, then the temperature profile can look something like that. And again, you can go through all the equations. You can go and from the continuity of conservation of energy, you can go and look at the energy terms of in the fluid and say it is equal to mCpTm. You're going to go through a derivation, and from that you can actually then derive the mean temperature, which is equal to 2 times V average multiplied by r squared, the integral from 0 to r, tr, ur, dr. So it's a little bit complicated than the fluid mechanics one in terms of the integration. But the bottom line for why we do it is actually to get the average temperature. So the yellow is called Tm, the mean temperature, which is different from the bulk temperature. The bulk temperature that is T inlet, and that is T outlet. Okay. The bulk temperature is equal to the inlet plus the outlet divided by 2. And normally we use this temperature, the bulk temperature, to get the properties of the fluid. So the rho, the Cp, the viscosity, etc. Everything, all the properties. Normally the nomenclature is of such a nature that it should be determined from the bulk temperature, not the mean temperature. Why? Because in heat transfer, this mean temperature is changing because there's heat transfer. So that is what's different. So if we look at the same tube, I'm going to make the diameter now smaller. And in this case, the surface temperature, that is equal to Ts. If we draw Ts like that, okay. Then the mean temperature, I'm going to draw it in yellow, is going to be that distance there. Okay. And as we go along the tube, that temperature is going to drop. So that is still Ts, but now this temperature is going to get smaller, and then even at its smallest, here at the outlet, because the heat transfer, Ts. Okay. So the mean temperature Tm is a function of x. It changes along the tube. It's not a constant. Let's look at the Reynolds number, and specifically for a circular tube. That is the circular tube. And we would like to determine the Reynolds number. Then it is equal to the average velocity multiplied by the diameter divided by the kinematic viscosity. You can write it in this format, or you can write it in the format of V of rho multiplied by the average velocity multiplied by the diameter divided by the viscosity. Let's call that equation 1. I'm going to use it just now. And then we can say, but the mass flow rate is equal to rho V average multiplied by the cross-sectional area and the cross-sectional area for the tube is equal to, what is the cross-sectional area of the tube equal to? Circular tube. Okay. So in this case it is equal to rho V average multiplied by the cross-sectional area is pi up 4 d squared. I'm writing it in another color for a very good reason. Okay. Now you can go and write the average velocity as a function of mass flow rate, and you can go and substitute it into this equation. Okay. So you can write V average is now equal to the mass flow rate divided by rho pi divided by 4 d squared. And let's put that into equation 1. And the result is that the Reynolds number can now be written as 4 times the mass flow rate divided by the viscosity pi multiplied by the diameter. You see that? Okay, so you would like to know, why do I specifically give attention to this? Well, as I've said previously, in most of the internal forced convection problems, the mass flow rate is given. And it is saving you a step of 2 to calculate the Reynolds number directly. So this equation is very important in your textbook. There is, however, a however. Okay. And what is the however? This is valid only for a circular tube. For a circular tube. Do you see? For the cross-sectional area, we've used pi divided by 4d squared. Let's suppose we make use of a tube which is like that, a distance a and another distance a, and let's call this equation 2. Then we can say from equation 2, then the mass flow rate is equal to rho V average multiplied by the cross-sectional area, and in this case the cross-sectional area is, in this case it is equal to a squared. You see? Therefore, if you go and put this into equation 1, you are not going to get the Reynolds number is equal to 4 times the mass flow rate divided by the viscosity pi d. You see that? So you have to be careful for that. This equation, very important. I would recommend that you put a marker or something there in your textbook. It's going to save you a few minutes in calculating the Reynolds number without the need of calculating the velocity, because we do not normally need the velocity. However, it's only valid for a circular tube. And there you can see the reason why. We've set the cross-sectional area, in this case, is pi divided by 4d squared. That is the result of this equation. If we now go and say the cross-sectional area is equal to a squared, then we are not going to end up with the same equation for the Reynolds number. Do you agree? Okay. Now, something else that is important and is what we call non-circular tubes. Non-circular tubes. With non-circular tubes, it will be tubes like the one that we've discussed just now, a square one of A in this direction and A in that direction, or it can be like this. That is distance B and that is distance A, or even in the case where we have something like this, an open channel. And that is equal to A, and that is equal to B. Yep.
For calculating the Reynolds number using the diameter of the tube. Okay, so for a non-circular section, would it be possible to use equation 85 if you calculate the hydraulic diameter?
I'm on my way to it, but no, you can't do that. Okay. So that's exactly the point I'm going to make now. So if you go and calculate the hydraulic diameter of a circular tube, you get the diameter. Okay? So for circular tube it works, but not for the others. Right, so for non-circular tubes, you've already done it in fluid mechanics. We make use of the hydraulic diameter, and the hydraulic diameter is 4 times the cross-sectional area divided by P, the perimeter. However, you have to go and read very carefully if you see that definition, because that P is the wetted perimeter, and that cross-sectional area is the real area for the fluid. Okay. So let's look at the case of a cross-sectional, rectangular cross-sectional area like that, one or other duct of dimensions A multiplied by B, and there's air or water flowing through it. So it makes all the surfaces wet. Then we can say that the hydraulic diameter is 4 times the cross-sectional area. The cross-sectional area is AB, you agree? Divided by all the surfaces that are wet. That's that one, plus B, plus A, plus B. So it is 2 times A plus 2 times B. You can go and get rid of the 2 to make it simpler. Now the other one is the one where we've got a fluid in a channel. So that's the fluid. And let's call that distance A. And that distance we call H, the height of the fluid. And that distance is equal to B. The hydraulic diameter is then equal to 4 times the cross-sectional area, but not that height. That height, it is the real area for the fluid. Okay, so it is 4 times HB. That is the cross-sectional area of the fluid, divided by the wetted perimeter. The wetted perimeter is 2 times H plus B. You follow? That's easy. Why is this hydraulic diameter important? Because we are busy with non-circular types of geometries. So for non-circular, we always work with the Reynolds number based on the hydraulic diameter, which is then equal to rho V average multiplied by dH, which is the hydraulic diameter divided by the viscosity. And we always work with the Nusselt number, dH. So the dH, I'm just putting there to indicate it is based on the hydraulic diameter, is equal to H multiplied by the characteristic length, which is the hydraulic diameter, divided by K. You follow? Okay. Paragraph 8.3 in the textbook is the entrance region. Now that's very important in internal forced convection. The entrance region. Now I've shown to you in many cases this sketch, how the flow develops in terms of the hydrodynamic boundary layer, which is the velocity boundary layer, is going to do that. And then the thermal boundary layer, which maybe is doing that. Okay. And one of the first things that I've explained when we've started with this lecture is that with internal forced convection, there are many cases where the two boundary layers meet each other. And that is going to be very, very important, because that distance we call LH. The length, how long it will take to get hydrodynamically fully developed. And similarly, the length that it's going to take before the boundary layer thermally fully developed. That is LT. So the one LH and the other one LT. Why is this important? For the following reason. If we look at the friction coefficient downstream the pipe or the tube, then there is the distance where it is fully developed. Okay. then the friction factor is going to do something like this. Okay. Here it is very thin, so the pressure drops are at its highest, and as it decreases, the pressure drop decreases. So in this first part, we are going to call this flow developing flow, and this part of the flow we are going to call fully developed flow. Developing flow and fully developed flow. If the flow is developing, then the friction factor is a function of x, a function from the distance from the inlet. While if it is fully developed, the friction factor is going to be a constant. So the friction factors that you've seen in the Moody charts are these values. It is for the fully developed flow. It is not for the developing part. Which means that in some cases, if you do not take this into consideration, the pressure drop of your duct or tube can be much higher than expected. So this distance there is equal to LH. That separates the developing part from the fully developed part. Now similarly, if we plot the heat transfer coefficients or the Nusselt numbers as a function of x, then that is the length that determines if the flow is fully developed or not. That is LT. And the result would be that the heat transfer coefficients or the Nusselt numbers would do something like that. In this region, we will say the Nusselt numbers is a function of x. There, the Nusselt numbers is constant, and the heat transfer coefficients are also constant in general. So again, the developing part, they're developing, and that part there, fully developed. FD, fully developed. Now, it is very important for us to know how long does the flow to take so that it is fully developed. And equations has been developed for it, and you should know this one. LH is approximately equal to 0.05 multiplied by the Reynolds number multiplied by the diameter. LH is that length it is for the velocity boundary layers to get fully developed. And LT is approximately equal to 0.05 Reynolds, and then we put something in there, Reynolds Prandtl multiplied by the diameter. And take note, this is for laminar flow. For laminar flow. Now this equation is a theoretical equation. Okay. If you go and look in the work of Meyer and Everts that we published this year, 2018, you will see that that length, if you go and meet it with experiments, you will actually see it is equal to 0.12 Reynolds Prandtl to the diameter. Okay. Now just take note of this. We are not going to use it like this in the textbook because it's going to cause lots of confusion. So for this module purposes, we are going to use those two values. But it is actually much longer than what was theoretically determined previously. So, using this equation, take note, not this equation, but this one. Let's suppose the Reynolds number is equal to 20. Okay. Then LH is approximately 1 diameter. Okay. Let's suppose the Reynolds number is equal to 2,300, so that is about a transition. Then LH is equal to 115 diameters. 115 diameters because before the velocity boundary layer will be fully developed. Okay, let's suppose the Prandtl number is equal to 10. If the Prandtl number is equal to 10, for again this case of a Reynolds number of 20, then LT would be equal to 10 diameters. And for this case of 2,300, LT would be equal to 1,150 diameters. It takes a long time before it is fully developed. So we can see that if the Prandtl number is larger than 1, if it's larger than 1, the temperature boundary layer will be much longer than that of the velocity boundary layer. Prandtl numbers, order of magnitude 10 is most liquids. Prandtl number of water is 7. Air is a Prandtl number smaller than 1. So for air, you're going to have the situation where these values, the LT values, is going to be smaller than those two values. So if the Reynolds number is approximately 0.1, the Prandtl number is approximately 0.1, this LT would be 0.1 diameters, and that LT would be 11.5 diameters. So it is much quicker before it is fully developed. Now take note, those two equations are valid for laminar flow. If the flow is turbulent, then things becomes much easier. Then LH is approximately equal to LT, and that is 10 diameters. So within 10 diameters, the flow would be fully developed. Okay, I'm not going to follow exactly the same order as in the textbook now. I'm going to do things a little bit different and add some other materials just to make things easier. And that is to introduce at this stage what I'm going to call heating and cooling conditions. And we're going to talk a lot about it. Heating and cooling conditions. So normally in the textbook or in this module, there will be two different types of heating and or cooling. Why? Because most industry problems can actually be put into one of those categories. The first category is where we've got a constant heat flux. Constant heat flux, and we indicate that with the H. The H indicates it's a constant heat flux condition. While in this case, we are going to have a constant wall temperature. And that is going to be indicated with a T. Temperature Ts is constant. So here the temperature is constant, there the heat flux is constant. With the heat flux, normally the amount of heating that we put in per meter or per millimeter is exactly the same. So that is our heat flux at a constant heat flux. And in this case, that is going to be Ts, and that wall is also going to be Ts if it is circular in nature. Right, so if we divide this sort of in two, if you can use the left-hand page to do what I'm going to do now, if you can put it there, and then there's also a right-hand part of the page. And you can do it like this. So this is still the constant heat flux case. Constant heat flux. And that is the constant wall temperature. Constant wall temperature case and the constant heat flux case. If we look at typically the Nusselt numbers, take note, this is for laminar flow, and that's a function of x. And this would also be the Nusselt number as a function of x. Oh, sorry. Constant heat flux and a constant wall temperature. So the Nusselt numbers is going to do approximately that. There it is fully developed. On the left-hand side it is developing. And to indicate that this is the Nusselt number for constant heat flux, we put an H there. Nusselt H. This one we indicate by Nusselt T. It's a constant wall temperature. And the result would be something like that. So you will see the trends are exactly the same. So you will ask me, but what is the difference? Well, many students, if they look at the graphs in the textbook, do not realize it when they look at it. But if you go and plot these two values now on the same graph, so it is Nusselt H and Nusselt T. The one for constant heat flux and the other one for constant wall temperature. Then you're going to see they do something like that. So that is Nusselt H and that is Nusselt T, and that difference can be in the order of plus or minus 20 to 30%. Now, that is for laminar flow. Okay, for laminar flow. If we would do the same for turbulent flow, we can plot the Nusselt H and Nusselt T as a function of x there. Then that distance is equal to 10 times 10 diameters. The Nusselt H values is going to lie approximately there. So this is turbulent. And take note, I'm drawing these values to a larger value in terms of the scale next to it. So that is going to be for Nusselt number H. And who would like to guess where the Nusselt number T line is going to be? Well, they sort of do something like that. And the Nusselt T line. So what is the bottom line? Okay, that is 10 diameters. And that distance LT is equal to 0.05 Reynolds Prandtl multiplied by the diameter. So what is the bottom line? The bottom line is that the type of heating and or cooling condition that is going to be used, constant heat flux or a constant wall temperature, has a significant effect in the laminar flow regime. Okay, but not in the turbulent flow regime. So normally, if you calculate the Reynolds number and it's turbulent, then you can say for yourself, yeah, I've got some less work to do. I don't have that much to calculate. It's easier. Any questions, you guys? You guys? Any questions?
Just wanted to find out, I missed what FD means.
FD, fully developed. Fully developed, I'm going to use it a lot, and that would be my shorthand for developing. And again, they're the same. From there, it is fully developed, and that would be for developing flow. The flow is developing. It hasn't become constant yet in terms of the Nusselt numbers. Okay? Any other questions? If not, ladies and gentlemen, then thank you very much. And I'll see you again on Thursday. Bye-bye.